So Irit, I gave many talks about this subject, but I gave one last year, and Irit asked me, it was a 1 hour talk, so Irit suggested that I give it in a 2 hour slot so that I can go slow over the many things that happen here, and it would be better. And I'm sure she is right. Of course, I use the opportunity to add material. Well, we'll see how it goes and how much I can do. So I want to tell you about this topic that with these co-authors listed here, we've been pursuing over the last 4 or 5 years. And the title changes as we keep understanding better and better what we are doing. Now it's Geodesically Convex Optimization, which reflects the last installment of work from the last year, roughly, and I hope to get to that. And I also promise to explain this subtitle about proving that P is different than NP using gradient descent. But we'll get to that. So as I said, it's a sort of survey. We started it about almost 5 years ago, and since then, both our understanding and the algorithms, the applications, and the connections that are being accumulated is more like a snowball. I mean, they are just it just grows and grows and grows. So there's a lot of material here. I'll start like I always start with this very simple problem that I'll define. In fact, a simpler one, but the one problem we'll focus in the first hour is the singularity of symbolic matrices, and one algorithm, which is the alternate minimization algorithm. And then we'll just internalize what we are doing. I'm more or less following the way, more or less the evolution of ideas in this project. And once we internalize, we'll generalize, and once we generalize, we internalize more, and we'll understand better and better what we do, and there'll be stronger and stronger results. And I hope to get to this geodesic optimization and describe it at least at high level. It sort of extends the standard Euclidean convex optimization tools and algorithms to the context of Riemannian manifolds that are defined by group actions, and give quantitative bounds to these algorithms. As I said, there are lots of connections and applications, and maybe I'll get to talk. I prepared slides describing some of them in some detail, but just in case we don't, there's a list, and just to impress you with the kind of mathematical areas that come into this game. Non-commutative algebra. You don't have to read the black thing, but just invariant theory, of course, will be a major thing we'll discuss. Quantum information theory, analysis turns out to, this work enables to prove inequalities. Some things have been added very recently by other people, like connections to operator theory and to statistics, that just in the last year managed to use these tools. Of course, for me, the motivation was computational complexity, trying to prove lower bounds and connections to de-randomization, which we will discuss. And finally, optimization, which is something I don't or algorithms, which I don't do so much of, turns out to be very important here. And in particular, it seems that these geodesic convex algorithms enable solving problems that it was not known how to solve before, some very non-convex problems like solving some families of quadratic systems of equations and membership optimization in some exponentially large linear programs. So we'll hopefully get to some of these. Back to the plan. So I want to discuss this one problem and one algorithm, and we'll actually have even a simpler problem and simpler algorithm before we get to the real ones, and this will be it. So I don't know how many people are there, but if something is really unclear, stop me. Otherwise, yeah, maybe we should, when we take a break, we can have questions also after the first hour. So perfect matching is a problem everybody knows. We are given a bipartite graph and ask whether we can match the left side to the right side. It's the same problem you have as parents, as you want to give candies to your kids, but not everybody likes every candy. And in this particular graph, there is a way to do it. There is a perfect matching in G prime. In this graph G, there is no perfect matching. So sometimes there is, sometimes there isn't. And one major aspect of lots of works in combinatorial problems is the ability to translate them to algebraic problems. So how do we translate this problem in algebraic terms? It's well known. We look at the adjacency matrix of this bipartite graph, the incidence of the left and the right. Put 1 when there is an edge, put 0 when there is no edge. That's the matrix A sub G. And the question of whether there is a bipartite match in perfect matching in this graph is the same as asking the question of whether the permanent of this matrix is positive. The permanent of this matrix, you see the formula in orange there, it's just like determinant, it's just without the signs. And it's very easy to see this fact because the permanent just goes over all diagonals and multiplies their entries. So it will be positive if and only if there's a perfect match. This problem is ancient and has efficient algorithms. Already in the 19th century, Jacobi found more or less the same algorithm we teach in class today. So it's a problem in polynomial time. Permanent may be a nasty polynomial, but just testing its positivity is not difficult. Anyway, the permanent is nasty, and maybe there is a better algebraic formulation of this problem. And in fact, Edmonds found one. And he suggested that instead of looking at the adjacency matrix of the graph, we should put variables wherever we see a 1 in the matrix. So we replace every 1 with a variable that's specific to the entry, like x11, x12, and so on. They never repeat. And once we do that, so this is already a symbolic matrix, Hg of x, right, of these variables. And his observation, which is again simple, is that the graph is a perfect matching if and only if the determinant of this matrix, which is a polynomial, is not identically 0. Okay, so it's very simple again, because if there is a perfect matching, there is a diagonal, you multiply the entries, it's a monomial, and since all the variables are distinct, we get a non-zero as a polynomial, despite the fact that the determinant has negative coefficients. Nothing can cancel a particular monomial if it exists. Now, this problem is equivalent to the perfect matching problem, so it's also in P. And the amazing thing that Edmonds did next was to ask the following question, to generalize it as follows. Suppose that instead of putting a variable in every entry of the matrix, we put a linear form. So forget the fact that beforehand matrices came from graphs. We can just, we had the matrices, symbolic matrices with variables in every entry. Suppose we just put a linear form in a set of variables in every entry and ask about the determinant. So we are working over a field. For us, the field will be the rationals or the reals or the complex numbers. One way to think of the like the input to the matrix, if every entry is a linear form, then we can write the matrix coefficients of every variable. So this matrix is A1 x1 plus A1 A2 x2, etc., where AIs are just constant matrices. And the singularity problem, the question that Edmonds raised, was if I give you a tuple of matrices like this, namely I define a symbolic matrix in this way, does the determinant vanish identically? So same problem we saw before, but now for general linear forms. This is a singularity problem. So what do we know about it? Edmonds asked the question whether, like the special case we saw before, it has a polynomial time algorithm, a deterministic polynomial time algorithm. And this is a problem we really want to solve, and we will not. But anyway, let's continue with what's known about it and why we care about it. One observation that was made once, randomized algorithms started to appear in the 70s was by Lovaas that this problem has a very simple probabilistic algorithm, which is efficient. The way it works is the obvious way. You just plug random numbers to the variables, and then you get a numeric determinant, and you just evaluate. This is simple. Of course, if the determinant was identically 0, you will never get 0 in this process. And if it was non-zero, then random numbers will catch a non-zero. That's basically the argument. So it's a very simple probabilistic argument. And so the question, you can think of this question of whether it's in P as a de-randomization problem. Next, different universe, even though it's the same year, Valiant showed that this problem is really important because it captures all algebraic identities. Basically, all algebraic identities in mathematics, those that are described by formulas, can be expressed as the determinant of a symbolic matrix. It's what we call the PIT, or the polynomial identity testing problem. And therefore, it's more interesting than it looks. It just it captures all algebraic identities. But it wasn't of course in mathematics there are many. I mentioned algebraic identities, but also it arises in many different ways in different areas of mathematics, in modular isomorphism, graph rigidity, and so on. And people are interested in solving this problem, but I think the importance of this problem did not really manifest itself so strongly until Cabanet and Impagliazzo discovered the following fact. It's not hard to prove, but it's really amazing. Somebody has their microphone off. Okay. Cabanet and Impagliazzo discovered the following theorem. If you have a deterministic polynomial time algorithm for this problem, then you prove the major lower bound. You have essentially separated what's called VP from VNP. These are the algebraic analogs of P and NP. So for those who've never seen it, it's sort of stunning. You look at the content of this theorem. On the left side, you see that there's a deterministic algorithm for some problem, an upper bound. And what it implies is a lower bound. in fact, a very, very strong lower bound. We are not close in any way to proving things of this type. And so an algorithm can prove a lower bound, can separate essentially P and NP. And that's one half of the subtitle I gave. We want to separate P and NP, or VP from VNP. And you know, they suggest that they can do it using an algorithm. Just find a deterministic algorithm. And this is what we will look for in this talk. We look for this and other algorithms for other problems, but that's essentially the beginning of the explanation of the subtitle slide. So that's what we want to do, and as I said, we will not do it because we would have heard already if we have succeeded, but still, let's look at this problem, singularity, and talk some more about it. So I want to tell you about the dual life of symbolic matrices. So we already said what a symbolic matrix are. L of x is this set of linear forms. And we are given, that's a computational problem, we are given the coefficient matrices, and we ask whether it is a singular matrix. We ask whether the determinant is 0, we ask whether it's a singular matrix. So I didn't explicitly say it, and I'm sure that's what you thought, and that's what I meant, is that the variables in this description commute. And if they commute, then the question is, what do I mean by, is the matrix singular? Is it singular in the field of rational functions in these variables? Is it invertible or not? And we said what we know about it, complexity, and this is the open problem that will remain open also by the end of the talk. But you can study this problem, and it was studied in the case that the variables don't commute. And the first question is, what does it mean to invert a matrix? Where do you invert it? And it turns out that there is an appropriate field in which you can, I mean, that's a natural home for the inverses of such objects. And I'm not going to describe it, so I'm not, in some sense, not defining fully the problem, but there'll be other definitions later, and you'll see that it's you'll see a definition of this problem. But anyway, you can just think about what happens in the non-commutative case, and people considered it and considered algorithms, and it turns out that even decidability in this case is not obvious. So this NC thing, I'll call the non-commutative singularity, it took effort and a big theory of non-commutative fields by Amitsur and by Kohn, eventually leading to an algorithm for it, just a finite algorithm. And so you see, it looks much harder. And the best upper bound that existed before our work was an exponential time algorithm by Kohn and Rethenauer. And the main thing I want to describe in this first hour is an algorithm with Gar, Gurwitz, and Oliveira, which is a polynomial time algorithm in the case of the rationals. And shortly after, a completely different algorithm, very algebraic algorithm, was developed by Ivanios, Sklar, and Subramaniam, which works for practically any field. And I will not talk about it. I will not talk about algebraic algorithms at all in this lecture. I'll talk only about this, what you will see as an analytic algorithm for the singularity problem. So this is a problem. That's a problem of singularity of symbolic matrices that we will address and solve. So we talked about the problem, and now I want to talk about the algorithm. So the algorithm will be a very simple heuristic called alternate minimization that I'll again demonstrate on the simple, on the toy problem, the matching problem, and then we'll extend it to this singularity of symbolic matrices. Okay, so here is our problem again. We know it's a polynomial time, finding a perfect matching in a graph. And I want to describe a very different algorithm than the algorithm that's, let's say, taught in undergraduate classes, the augmented path algorithm. And for this, I need another equivalent form of the perfect matching problem, which doesn't quite look like it. This is a matrix scaling problem. So it's a very old problem. Synchron is very associated with it, but it, even in the 30s, people considered it. So let me tell you what it is. The input is a non-negative matrix, like with the perfect matching or permanent. And I'll remind you what a doubly stochastic matrix is. It's a matrix with row sums 1 and column sums 1. And maybe our matrix is not doubly stochastic, so we want to make it doubly stochastic. And make it how? What are the rules? What are we allowed? We are allowed to multiply rows and columns by scalars. Okay, so just change the weight simultaneously on all elements of a row, all elements of a column. So in other words, we are allowed to pre and post multiply the matrix A by diagonal matrices R and C. And the question is whether with these operations we can scale the matrix, we can make it doubly stochastic. So the problem is find whether there exists such diagonal matrices so that the product has row columns and row sums and column sums approximately 1. I want to stress this approximately 1. You can ask for making them exactly 1, but I prefer, as you'll see, to ask them to be approximately 1, which with the meaning that you know, for every epsilon, that how close you want it to be, there exist such matrices that approximated to that epsilon. And the reason this is the right definition for us is that this is exactly equivalent to the question of whether the permanent of A is positive, whether there is a perfect match in A. Okay, so even though it looks very different, it's exactly the same problem. It's not so hard to prove. You can do it, and in fact, we'll see a proof. But people were studying for completely different reasons, and many reasons. They arose in the scaling problem, arose in numerical analysis and signal processing, and later for algorithms for approximating the permanent, and so on. So people scale matrices all the time. People who do linear algebra on computers scale matrices before they solve them, and so on. So there are many reasons to scale matrices, and that's what we want to do now. And if we do it, we'll also solve the perfect matching problem. So let's look at this problem. Let's take a particular matrix, a non-negative matrix, for example, one that arises from some bipartite graph. And we want to scale it by multiplying rows and columns by constants. And it looks like a non-trivial problem because, you know, they conflict. You can, you know, it's hard to do simultaneously. And the brilliant, or you can say naive, stupid, ingenious idea of Synchron and others was that, okay, it may be hard to do simultaneously, so let's do them one at a time. Let's make the row sums 1, and then later the column sums. Okay, so let's try to do it. Here's a run of this naive algorithm. Here we scale the rows, so now all the row sums are 1. We multiply the first row by 1/3. But of course, the first column is not scaled, so we can fix that and scale the columns, but now we ruined the row sums. We can fix the rows, and now we screwed up the columns. And if you do this for a while, you see that it converges. Well, it doesn't converge. It just alternates between these two configurations. It doesn't converge. So that's what happens when you run this algorithm on this matrix. It does not converge. On the other hand, the graph that we started with zero permanent. It had no perfect matching, so maybe it's okay. Maybe we need to look at another example. But before we look at another example, let's just write down what this algorithm does in general. So we get a non-negative matrix. We try to make it doubly stochastic, so we can, very simple to write down what we have. We just, if R of A is the diagonal matrix of the row sums inverse, multiply by this matrix scales the rows, and similarly with the columns, and we just alternate them. Just alternate scale the rows, scale the columns. This is what is, these are, if any of them are zero, we know it's impossible. And this is really the alternate minimization algorithm. You have a problem that has several parts, and maybe the problem is difficult, but each part is easy. So you solve each of the easy parts and just repeat it for a while. That's the alternate minimization algorithm. And let's try to apply it now to a different matrix. So here's another matrix. That's a matrix of this graph, which did have a perfect matching. And let's see what happens. So we scale the rows, and then we scale the columns, then we scale the rows, and you can probably see that the diagonal entries are increasing and off diagonals are decreasing, and indeed what happens in the limit is you get to this. And so it does converge. And it converges for a graph that had a perfect matching, and this is no accident. These two things are no accident. So let me tell you what happens in general. Here's the algorithm, and I'm going to give you a full analysis of this algorithm because it's a simpler one, and so lots of what will happen later will just generalize this. And I'm giving you a particular analysis from a paper that I wrote with Lina and Samornitsky about 20 years ago. And it's really lucky that we did this. I mean, I mentioned that many people discovered this algorithm, the problem and algorithm, and so did we. We didn't know about this past work. We needed something to we developed a deterministic algorithm to approximate the permanent and via matrix scaling. And because we didn't know it, we also found an analysis that was different than previous analysis. And this was really absolutely key to what will follow. So let me first finish the algorithm. So we scaled, we do it, we run it about n squared times, these iterations in this case. And then what do? Let's say the last step was normalized. Well, we basically test that both row sums and column sums are very close to the one vector in any norm you like. One of them will be exactly one, right? Because let's say the last step was normalizing rows, and we check whether the column sums are very close to one. And if the answer is yes, we declare that the permanent is positive, there is a perfect matching, and otherwise we declare that it was zero. There's no perfect matching. And the analysis of this algorithm, as I said, is very simple, and it proceeds more or less like you would for any dynamical algorithm or process of this sort. You pick a potential function, and in order to prove convergence, you just show that this potential function, let's say, increases, but is bounded and therefore has few iterations. And the analysis that we use takes as a progress measure the permanent function. So we show that the permanent is an appropriate choice. And then, like in each one of such proofs, you prove the following 3 steps. You prove a uniform upper bound on all the matrices in the sequence. So let's say the sequence of matrices produced by this algorithm is A1, A2, and so on. Prove that all of them are, the permanent is bounded on all of them. You prove that every step increases the permanent. If there is room to grow, this green star says there is room to grow. And you want to prove that if the permanent is positive, the answer should be yes. Then, in fact, you start from a matrix that's not, where the permanent is not too small. So the number of iterations will be small. In this case, it would be, I don't know, sample, maybe n squared steps. And these are all easy, but let me show them to you. And it is, I highlight the last step because as we proceed to the real problem, it will not be so easy. Just this last step. The other steps will be the same. And as a comment, people like us who teach undergrad algorithms usually teach a very different algorithm for perfect matching. I suggest teaching also this one, A, because it's so simple, B, because it's so simple to program, just 2 lines of code. And let's see, the analysis is very simple. So what's the analysis? Here are the three steps. Let's say that the sequence of matrices produces is A1, A is A0, A1, A2, and so on. Well, we'll do it in some other order. The last step, I mean, the fact that there is a lower bound is very simple. If A had a perfect matching, then after the first scaling operation, all the row sums, we normalize the row sums, but these ones became something at least 1 over n. And so the permanent, I should have written n factorial instead of n squared, but can I change it? Okay, the permanent is at least the product of these entries, so it's at least 1 over n factorial. And it's an important point that an exponential boundary is fine because we are growing by 1 plus 1 over n, so maybe I should take n cube operations, and then we have convergence. So proving this lower bound is very easy, as I promised. For the next 2 steps, for just a second. Okay. For the next 2 steps, let me call, I want to argue about the particular iteration between AI and AI plus 1. So let me call AIB and AI plus 1C. And let's say the last step was normalizing the rows. Let's say that B has all rows, the row sums are 1. And the column sums are something, some vector. Okay, so let's look at the first claim, the permanent of any element in the sequence, like B. Well, the permanent is always at most a product of the row sums. That's very easy to see. And here, all the row sums are 1, so the product is 1. So we have this upper bound. And the most interesting case is 2, but it's also very simple. So let's see what happens when we move from B to C. I claim that the permanent increases, so let's look at the permanent of C. How was it obtained from B? We just multiplied by the inverses of the column sums, product of 1 over UIs. And we see a product, suggests arithmetic mean, geometric mean inequality. And so we can put the sum of the UIs over n. But what's the sum of the UIs? The sum of the row sums is the sum of the column sums is the sum of the row sums. So it's n. So this is just 1. So we see that the permanent of C is at least the permanent of B. It's not quite what we wanted. We wanted to show increase. But if there is room to grow, if the column sums are still far from being uniform, then we know that because the AMGM is tight only when all the numbers are equal, we have a slack here, and we get that we grow by, it's a simple calculation to see that we grow by 1 plus 1 over n. Okay, let's look at time. Good.
Avi?
Yeah.
So you showed that it was an algorithm for perfect matching, and in fact that the matrix that you converge to has the perfect matching, right?
Yeah.
If there's more than one perfect matching, what will the matrix end up looking like?
It's very easy to see. It will basically all the entries. So as you see, well, if it was a 0-1 matrix, all the entries which correspond to edges that participate in no perfect matching will go to 0. All the other entries will remain positive. What is the meaning of these positive numbers is a very mysterious thing. You can hope, you would have hoped that those who disappeared belong to no perfect matching, that those who remain alive, if you see something that has 1/7 in it, you would hope that this is an edge that participates in 1/7 of the perfect matchings. And that would give you, of course, an algorithm to compute the permanence, or at least to approximate it. A deterministic algorithm. We don't know such an algorithm, and in fact, this is not the right interpretation. It's a big mystery. I spent some time on it, and it's a really good question. I want to point out that, of course, the algorithm works also if it's not a 0-1 matrix, but just simple to do the analysis. Otherwise, you can have arbitrary rational numbers, and the convergence will be still polynomial in the length of the entries. And in fact, in this paper, one of the new things that we did was also give a strongly polynomial time algorithm that does not depend on the length of the rational entries. But anyway, that's a digression. Any more questions? Okay, so now I want to get to the real problem. This was a baby case, as I said. And the real problem, well, yeah, one comment I want to make, because later we may talk about this. There are non-uniform scaling questions that people have been looking at. Instead of asking to scale a matrix to the uniform vectors, all equal row sums and all equal column sums, you may give other target vectors, and you can ask about scaling. And there are reasons to do this. In particular, it's related to max flowing graphs, and it's sort of an important special case of marginals problem, where, I mean, you can think of a matrix as a two-dimensional distribution, and you are trying to scale it to have particular marginals. So we may talk about this later, but I just want to say that the same algorithm works and converges fast, and that's simple. So now I want to talk about the real problem, and the real problem is this non-commutative singularity, which you can think of as a generalization of bipartite matching, and an operator scaling algorithm, which is a generalization of the matrix scaling. It all starts with a paper of Gurwitz, which happened just a couple of years after LSW, and was stuck until this analysis we gave in this paper about 5 years ago. But I want to describe first Gurwitz's ideas and his algorithm. So Gurwitz made a quantum leap, and it's a pun which is intended. If you hoping not to insult any physicists in the audience, but here is how you quantize a problem. You quantize a problem by just more or less increasing the dimension of everything by 1. So we have a matrix here. the positive matrix will move to a tensor, positive operator. I'll describe what it is. When you quantize, you move typically from L1 to L2. There's a meaning to scaling a tensor, or scaling an operator. So row sums and column sums equal 1 in the three-dimensional world, or when you have a set of matrices given, is that some AI transposes the identity, this sort of scaling the rows, and some AI transpose AI is identity, sort of scaling the columns, it's the analog. And what are the scaling operations? Here we had on matrix scaling, we had diagonal matrices, right? And these are basically vectors. So you generalize vectors to matrices, to invertible matrices. So the allowed scaling operations are pre and post multiplying by invertible matrices. So far, it's just syntactic. I mean, it's sort of just sort of an automatic way of quantizing something. But Gurwitz gave meaning to all of this. So let's look at the meaning. So, and also the reason, not just the meaning, but the reason. So Gurwitz was really interested in solving the Edmonds problem, the singularity, the commutative singularity problem. I'll remind you the problem. We are given a tuple of matrices, right? And it defines a symbolic matrix L. And we asked originally whether L was singular in the commutative case, and later we asked whether it was singular in the non-commutative case. And what Gurwitz observed is that a tuple of matrices has, many meanings. Here it was just coefficients of a symbolic matrix, but in quantum information theory, a tuple of matrices is really a positive operator. That's how you should think of it. This tuple of matrices, think of them as an operator, let's call it L of P. The input to it is P, a matrix, and it acts on the matrix by multiplying on the left by AI and on the right by AI transpose. Okay, so it's a linear operator on matrices, and it's called positive because if you feed it a PSD matrix, you get out a PSD matrix. So in quantum information theory, these PSD matrices would be density matrices, and that's the most general, basically the most general quantum operation or noise operation you can have. Okay, so we have this, there's a meaning, and there are questions about positive operators. As I said, there's a meaning to double stochasticity of operators, and it's written again here. And one interpretation is just when you feed the identity matrix to the operator and to its transpose, to its dual, you get back the identity. And this is meaningful in quantum information theory. And basically, we talked about how to scale such matrices. And the question is the ability to scale, what does it tell us? And Gurwitz has several characterizations, but he basically wanted to solve the singularity problem. And he managed to, so that's basically the operator scaling. And he managed to prove that, well, I wrote it in reverse. So you cannot scale an operator. If you cannot scale L, it means that as a symbolic matrix, it is singular. So he managed to prove one direction. And he didn't manage to prove the second, the reverse direction, and actually because it's not true. So it's basically not the right problem to look at. And one of the starting points of this work was realizing that if you look at the non-singularity of symbolic matrices, then it is equivalent to not being able to scale that. So That's indeed why we can solve non-commutative singularity and cannot solve so far the commutative singularity. But let me proceed with what Gurwitz did. He basically suggested that we run the scaling algorithm, and let's see what it does. So you don't have to read it. It's exactly the same algorithm as in the matching case. You scale rows, scale columns. You can easily compute what are the non-singular scaling matrices you need in order to scale. They are written down there, but you don't have to read it. And the hope was that you run a polynomial number of steps. It was not clear at this point why. That was the hope, but you run it a polynomial number of steps, check whether you are close to being doubly stochastic in this sense, and as before, answer yes. If it's close, just say yes. It's non-singular, and if it's it's not close, it didn't converge, then you say that it's singular, just like before. And the question was how to analyze this, and you need a potential function. And again, he gave an ingenious choice. He tried some version of quantum permanent, and it didn't work, but another progress measure called the capacity did work. Again, no particular reason to remember it, but I'll tell you what it is. It's basically a very natural notion. You look at the ratio between the input of the operator and the output of the operator, right? Or the output over the input, over all PSD matrices. The reason he chose it is that it has the same properties that we wanted. First of all, it's related in exactly the same way as the permanent to the answer. The capacity is positive if and only if it's non-singular. I mean, this requires, he didn't talk in these terms. He talked in different terms, which I will not explain. But anyway, it holds that capacity is positive if and only if it's non-singular, and it's zero if and only if it's singular. So that works. And the analysis also is happy with this choice of capacity. All capacities are bounded by 1. As before, capacity grows non-trivially when it has room by the same AMGM argument. And you just need an exponential lower bound on the capacity in the beginning, right? So you want to prove that if it was positive, then it's non-trivially positive, like before. It was n factorial before. Any bound like 1 over exponentially n or n to the c will do. And this was a hard thing, and this he couldn't do, so he couldn't analyze the running time of this algorithm and left it open. And this is what we did in this paper. So I want to give you a proof of this, and this will have to wait. Let's see with time. Okay, good. This will have to wait to the second half, because I'll actually give you a proof of this in a much more general context. But the ingredients, and this is the reason that it's hard and it's not simple as before, is that you need various mathematical tools, basically tools from invariant theory. You need to understand that what's happening in this algorithm is that they evolve by group. There is a group action here that's easy to see, and we'll talk about it more. And group actions have invariants, and the analysis uses degrees of this invariant polynomial. So we'll elaborate on this after the break. So let's just let me just tell you something else before we break. I mentioned that, so it's about these amazing connections, right? I mentioned that Gurwitz observed that a couple of matrices, can have two different meanings. I mean, symbolic matrices and also a positive operator. But in fact, tuples of matrices or tensors, it's the same as a tensor, arise in all sorts of fields. And in fact, you can ask natural questions in these fields about these tensors. Not only you can ask, I mean, these problems were being asked. And in some cases, they are very important problems in these fields. For example, the fourth problem, which is basically our singularity problem, is related to the word problem in non-commutative fields. Maybe the most basic problem about any algebraic structure, whether two objects in it are identical or not. And the sixth problem, well, let me make my point first. So you have these different problems in different areas, and it's sort of amazing. And this came out, I mean, all of this was essentially known, even if hidden in various forms or had to be extracted. All the first 5 problems are equivalent. So, I mean, somehow this, to me, was an amazing revelation that we definitely arrived at it through this work. Equivalent, I mean, not polynomial time reducible to each other. A tuple of matrices has property, has an answer yes to question 1, if and only if it has an answer yes to the question 2, and so on, up to 5, even though these are completely different questions in nature. So, yeah, I find it pretty amazing. The 6th problem is an analysis problem. It's about proving Braskamp-Riemann inequalities. And this turns out to be just a special case of all the other problems. So it connects even to analysis, not just algebraic problems. Okay. Because of this, because they're all equivalent, we automatically get polynomial time algorithms for all of them. So that's for free. Okay, so let me suggest that we take a 5-minute break, and then we'll proceed with getting a bit technical and learning about invariant theory. So 5 minutes, it's, I have 11:23. I don't know what you do when you take a break, but I'll just disconnect my video, bring up the talk. So I said that to analyze this algorithm, we need tools of invariant theory, and I'm going to give you the minimum I can give you about invariant theory. That for this talk, I should say that this project made me start giving survey talks about invariant theory, and you can find some on my website. So invariant theory studies symmetries, or in other words, group actions. And let's see some. Here, a group acting on graphs, on the labels of graphs. Here is a symmetric group, right? We permute the names of the vertices, and we still get the same graph. You probably have seen this billiard table. You push the white ball, and basically the group acting here is time. You let time evolve, and it changes the configurations on the table. Here's another one. You can take a shape, and you can just cut it and move pieces around, let's say, without overlapping them, and you get other shapes. It's also a group in some sense, because you can take inverses and it composes. So, although I don't know how to define this group. Anyway, when you have these group actions, there's a basic notion of an orbit. So we'll talk about this in more detail. We have the basic notion of an orbit, which is all the configurations you can get to using the group action, starting with any one. Okay, that's an orbit of, let's say, of the graph. And despite the fact that it's a lot of configurations, and you can think of it as a maybe dynamical system, like in the case of the billiard, some things don't change, and that's the content of invariant theory, which parameters of the systems don't change. So these are called invariants. And let's look at this, these examples. In the cutting and pasting shapes, the area doesn't change. That's easy to see if we don't overlap. And in fact, one can prove that that's the only thing that doesn't change. So in invariant theory, we want to understand all invariants of a process, of a group action. In the case of the billiard, you probably know from physics that there are only two invariants that are that don't change. Is for elastic collisions, it's energy and momentum. No matter what configuration you have, these two parameters remain the same. And in the case of this graph isomorphism problem, of course, we don't know. It's complicated. Okay, so I want to in this rest of the talk, the groups we will talk about are linear groups of matrices that act on vector spaces. It will always be over complex numbers. And these red stars indicate that I will cheat a lot in that I will not specify all the time which groups I mean and what actions I mean. But generally speaking, we'll talk only about reductive groups. These include, you know, much of the groups you know and love, like the general linear group, special linear group, classical groups of matrices, orthogonal group, and so on. And the actions will be, you know, rational actions. So these again will be actions of the type that you would anyway invent or think about, unless you're an algebraic geometer and there are weirder things. We'll talk about, I mean, these such actions have polynomial invariants. So the invariants can be described by polynomials. And the algebraic side, and there's a geometric side, especially when you work over C, of such group actions. And we'll talk about it later, about non-commutative duality, but not for now. So I want to talk about the basic objects of the algebraic invariant theory. So we have this action, group G acts on a vector space. And if it acts on a vector space, it acts on polynomials in these k variables that you know, describe an element on a vector in this space. So polynomials in these variables. And that's one basic thing. So an orbit of an element in this vector space of a vector GV is everything it can get to using, you know, when moved by a group. And because we are over C, it's also natural to look at the closure, all the limit points, add all the limit points of an orbit. So this is the notion of an orbit. Now the notion of invariant polynomials or invariant ring of polynomials. These are simply all polynomials that, you know, in f of v, that remain invariant under the action of a group element. So they don't change their value regardless how a group element acts on V for all V and for all G. So I want to give you examples. This is called the V sub G, that's invariant ring. It's very easy to see that's closed under addition and multiplication, so it's a ring. Let's look at some examples. If G is a symmetric group which acts on vectors, just permuting coordinates, then I'm sure you know that the invariant polynomials are simply the symmetric polynomials, and moreover, they are generated by the elementary symmetric polynomials. This ring is generated, this algebra is generated by the first n symmetric polynomials. Here's another example closer to us. Suppose that you act on a vector space which is a set of all matrices over a field. Okay, and you act by changing bases on the left and on the right by determinant 1 matrix. So you just change the basis by multiplying by R on the left and C on the right. What are the invariants here? What happens if you change bases on the left and the right? What polynomial in the entries of the matrix remains invariant? That's also clear. It turns out that it's the determinant and just all its powers. There's nothing else that remains invariant. Okay, so that's another natural notion. Here is an absolutely fundamental result to us. These invariant rings have infinitely many polynomials, but Hilbert proved that for our groups, they are only always finitely generated. Like in these examples, there's always a finite set of polynomials that generates all the others. For this purpose, for this paper, he developed what everybody's familiar with, the finite basis theorem, the Nussdalza theorem. They were all aimed to prove this result. Of course, they found many other applications. Once you know that they are finally generated, it's interesting to ask what's the largest degree you need to generate them. Like in those two examples, n is the answer. But in general, this is not true, and we'll see some results about that. That will be important to us. The last basic notion I want to talk about is a null cone, mainly because all our problems will end up being a null cone problem. So what's the null cone of an action? It's all the, let me see, yeah. It's all the elements that all invariant polynomials take to 0. All non-constant invariant polynomials. If you have a polynomial which is a constant 1, it cannot be 0 on anything. So again, it's all elements in the vector space that the all invariant polynomials make 0, and it's again crucial for us is that there is an analytic description to this set. So this is a variety. There's an analytic description. It's also all the elements in the vector space, so that if there exist elements in the group that push the vector to 0, or the norm of the vector to 0. So that's why it's called the null cone. Let's look at these two examples. In the case of the symmetric group acting on permuting coordinates, you can get 0 only if you start from 0. Permuting coordinates doesn't do much. It's a finite group anyway. It's not so interesting for us. In the second example, what is 0 of the determinant? Which matrices? It's all the singular matrices. And it turns out that singular matrices you can pre and post multiply by determinant 1 changes of basis that drive them to 0. That's a nice exercise if you want to do it. Anyway, this is a very important connection. It makes the analytic structure and the algebraic structure relate to each other, and we'll use it. Okay, so these are the basic notions from invariant theory. I wanted them, now let's use them. So we are going to unify and generalize what we saw before in the operator scaling. Here is the picture we had before. These are the two problems we already solved. And I want to generalize so some things in this picture. So first I'll talk about the alternating minimization algorithm that we saw in these two cases. We'll generalize it. And we'll generalize it naturally to groups because the action, I mean the scaling, the rules for scaling were actually allowed to, in both cases, to apply group elements. In the first case, it was diagonal matrices from the left and the right. This is what I call Tn. It's a torus of length n. On the right, in the operator scaling, we are allowed to apply general linear groups, such as GLN, called GLN, on the right and on the left. What else is there to generalize? We saw that for both algorithms, there was some maybe ingenious choices of potential functions, and we want to ask what's, how to analyze such algorithms in general, what would be good potential functions. We'll see this. And, scaling in the first case arose from, I told you, from various considerations in linear algebra and numerical analysis. It arose in operator scaling because Gurvitz wanted to solve singularity. What are scaling problems? We'll see that they are really interesting problems, and we'll understand them better. Okay, so let's start. Generalize the algorithm. So alternate minimization is a very, very common heuristic. It appears all over the place: statistics, optimization, machine learning. In general, as I said before, you want to solve whatever it means, optimize, sample, whatever, a function in some number of variables, let's say k. And this is a difficult, maybe non-convex problem, but in many of these cases, if you fix all but one coordinate and just try to optimize or sample or solve the problem in just this one coordinate, then it becomes very simple. So it's all over the place, and many of the cases we just use because that's what we can do, but we don't understand if they converge or they converge fast. And so we want a group version of this. This is a generalization of what we saw before, and here is the alternate minimization of groups. The framework is what you would expect. We generalize the picture we saw before. So we will have a product of groups. They are each either the special linear group or the special torus. Special, it just means determinant 1. And it acts on a tensor. So different components act on different directions in this tensor. So just a natural generalization of what we saw before. And the problem, as before, is given a vector in this vector space, a tensor, scale it. And again, like before, there are uniform versions, non-uniform versions, and we'll discuss them. And the main message is that everything generalizes. So, yeah, I should have stressed that this non-convex problem. In fact, it's not clear what, even the domain is a product of groups. It's not convex. And despite all of this, there's a theorem generalizing everything we saw before, is that if we alternate, solving the problem in each coordinate, which is easy to do, then in polynomial number of steps in the relevant parameters, you get to something which is epsilon scale. And so we'll talk about proving this as we'll prove the operator scaling. So I'll put it again before, next. So again, because I want to talk about the analysis. So first, again, the goal, I'll give you a tensor, and you want to scale it. And it will turn out that this will be possible if and only if this vector is not in the null cone. So this is related to the characterization we saw before, and this should remind you that we could scale a matrix if the permanent was 0, right? That's and we could scale an operator if the capacity was 0. It's the generalization of that. So we want to scale a tensor. Yeah, question?
You couldn't scale it if it was 0.
You can scale it if it's not in the null cone. You can scale it whenever it's not 0. When the permanent is positive, you can scale the matrix. When the operator is, capacity is positive, you could scale the operator, right?
Yeah, you just said it in reverse.
Oh, maybe I said it in reverse. Okay, thanks. So first I want to mention that this kind of problem has many more applications because many applications talk about higher dimensions. We mentioned k equals 2 matrix scaling, operator scaling. K equals 3, it captures what's called asymptotic Kronecker coefficients in representation theory. In any case, the entanglement distillation problem, let me not describe them. Slice length problem. There are many problems in different areas that fall smack into this framework. And as I said, we can solve this problem in this number of steps. And I want to stress that this polynomial time is not always enough. In some cases, you need, epsilon needs to be exponentially small to really answer this question. So it doesn't mean we solve all these problems in polynomial time. Often, some of these problems require double exponential time initially, so it does improve. But anyway, I want to stress this. So what's the analysis? The analysis turns out to be exactly the same as in the previous 2 examples. And the potential function is suggested by the fact that the vector is if it should fail, if you can't scale, it's simply the L2 norm of the vector. So somehow we automatically get, you don't need to be clever, you automatically get a potential function. And the way it works is as before, there are 3 steps. The bound on the element throughout the process is easy, the growth is easy, and the difficult thing which requires work, and I'll give you a sketch, is that if V is not in the null cone, namely it cannot be driven to 0, then not only you know that it and its elements in its orbit cannot have value 0, but you want a lower bound that will supply a convergence analysis in polynomial time. So we want to prove this, this bound. So how do you prove that if you can drive it to 0, it has to be at least exponentially big? And here we use the, so I'll give you a sketch in the next slide, where you use invariant polynomials. So let's see. So that's what we want to prove again. It's not in the null cone, then it has the norm has a lower bound. And every element in the orbit has the same lower bound. These are the tools. Well, we mentioned the Hilbert-Mumford theorem, right? It's something is in the null cone if and only if it vanishes on all non-trivial invariant polynomials. And so how can we use this? Well, if we had, so it's not in the null cone, there is some polynomial, and we want to use the fact that this polynomial doesn't vanish. We can assume it's an integer polynomial. It doesn't vanish, gives an upper bound, gives a lower bound on the norm. And that's very simple if you have bounds on the degree and the height of the coefficient size of this polynomial, right? I mean, I should say that before that, this work, I mean, you could solve the null cone problem or the scaling problem just by trying all invariant polynomials or all generators. But this leads to at least doubly exponential algorithm. So for us, this will be used only in the analysis because the algorithm I showed you is just alternate minimization. So there's an integer polynomial. So what do we know about it? Suppose the degree is some d and the height, the coefficient size is some h. Well, we know that it's an integer polynomial. So when we evaluate it on v, it's at least 1 because of integrality. And on the other hand, how many coefficients such a polynomial has? N is here the dimension of the group. It's d to the n, that's roughly the number of coefficients. Each coefficient is of size h. And then when you evaluate a monomial on a vector, then you get at most the disk power of the norm. So you can see that you can use it to get a lower bound on the norm of V. And the question is, how lucky do you get with this? And one important lucky result is that of Jerksen from about 20 years ago, is that all these invariant rings that we are talking about of reductive groups generated in degree at most exponentially n squared. And the other thing that we need to prove is bound on height on the coefficients of all these polynomials. And it turns out that for this you use something, one of the earliest papers in invariant theory, maybe the paper creating it is that by Cayley, where in particular he defines an ingenious process called the omega process for generating invariants. And then you need to study it and see what it does and prove an upper bound on the height. And if you combine this, I won't do it here, then you see that you get the lower bound that we want. So this is that's the whole analysis of all these alternate minimizations over groups. Maybe I'll ask for questions. No. Okay. All right. So good. So we have another. Yeah.
So you get that you get a bound that's doubly exponential, if I understand correctly here?
No, you get a polynomial. No. Notice that you grow when the lower bound is exponential, and you grow by 1 + 1 over n every step. You converge in polynomial number of steps.
But what is this v to the power d? And d itself is exponential.
Yes, but notice that if you can do the math, you will take a diff root of something that's d to the O of d. And the d will disappear luckily.
Okay.
So you don't. I mean, you can do the math. It's I didn't cheat you here.
Correct.
Yeah, so you get the right bound, and it works. It's amazing that an exponential upper bound is enough. It is amazing, but it works. So the important thing, as I mentioned, all this happens in the analysis. The algorithm doesn't need to know about. So okay, so we have an analysis, so we know that it works. But so what? I mean, what's going on here? I mean. We don't really understand what's going on. I mean, I told you this are non-convex problems, and I gave you the algorithm. It's a very simple, greedy algorithm. How come it converges? There must be a reason. So we'll answer this. I promised to tell you what are these scaling problems exactly. And the last thing is, what do you do, if you have some group action, it doesn't come very nicely equipped with a partition, and it's not does not support alternate minimization. So we'll see what to do about that as well. Okay. So we generalize more. And I'll tell you about non-commutative duality and geodesic convexity and the moment. So again, back to our picture, these were the examples. And now we are going to do something strange. we had, until now I described everything as where the goal was scaling, and the analysis used this potential function, one of these potential functions. And now we are going to switch the analysis with the goal. I mean, maybe we want to minimize this potential function. We saw it's important, the L to know, right? It's important to understand the null count problem. Okay, so here's the setup. We have, again, Gx on a vector space. And we are given a vector v, and we want to compute the following optimization problem. F of v is simply the infimum of the norm of gv in this in the orbit. Okay, so you have a picture there. We are given v. You see the whole orbit, and we are looking to find the lightest vector that we can in the orbit. Right. In particular, we know that if it's a non-convex problem, I mentioned that the answer will be 0 if and only if v is in the null count. And we saw that solving null count problems is interesting. We saw many examples. So, okay, how do we solve this optimization problem? Now, G is a general group. It doesn't have to be a product or anything. So here's a more basic question. If you look at this goal, and for complexity theorists, it's, at least morally, it's an NP problem. So if the answer is yes, if the infimum is 0, then we can supply a sequence of elements. There is a witness. There's a, not in complexity terms, but at least in spiritual terms, there is a sequence of elements that will show you that it gets smaller and smaller. For every epsilon you give me, I can give you a certificate that the norm is smaller than epsilon. So here's a question that complexity theorists would ask, and is how do you certify that maybe the answer is not 0, so it's positive? How do you certify it? And you already said it's bigger than 0 if and only if some invariant polynomial is not 0, but this is a very expensive certificate. So it turns out that this question was asked by invariant theorists, and they gave an answer. That's a fundamental theorem of geometric invariant theory. And it says that the answer to the optimization problem is positive if and only if there is some non-zero vector in the orbit which has a 0 gradient. So this mu is called the moment map. It's just at this point, think of it as, I'll define it next, think of it as just a non-commutative analog of a gradient. So there is an answer. Something is positive if something else is 0. So there is a witness here. This V star, I can give it to you, and you check that it's not a 0 vector, and nevertheless it has a 0 gradient, and that's your witness. So the problem is also morally in CoNP. So that's good. And in fact, there are several messages here, I mean, many, and we'll talk about them one by one. One will see soon that this problem, it will follow from this, minimizing mu instead of minimizing f is a scaling problem. So scaling problems somehow arise naturally, even without the motivations that other people found for them. Another message is that this theorem is a vast generalization of LP duality. So LP duality is a very special case of this for the case that the group G is an abelian group, basically a torus. Okay, so it's a vast generalization of LP duality. And the most important for the sequel for the next half hour is that what's going on here? I mean, how can such a if and only if condition hold? Having a 0 gradient is a local condition, right? It means that slight perturbations to the vector V star increase it. So it's a local minimum. But why should it be a global minimum? We asked whether we can, F can reach 0. Why is it a global minimum? So the answer is always, whenever you see this kind of thing, the answer is always the same. There must be some convexity going on. And we'll talk about this. This is geodesic convexity. And it just sort of lifts or extends the normal convexity that you know and love to Riemannian manifolds. These are the manifolds defined by our groups. Our whole optimization problem happens over our groups. So I want to explain this. So first, let me tell you a bit more precisely what is a moment map. I will not do it completely precisely. But just summarizing this slide, this existence of convexity intuitively explains what a local greedy algorithm like alternate minimization succeeds. And it also suggests extending, this, the case that you don't have a product structure, how to extend the results to other actions, because we know convex optimization in the Euclidean case, and we can try to extend it, which we'll do. Okay, so let me do them one by one. The moment map is, really exactly the same as a gradient. You just want to see if you are given a point V, a vector V. You want to see how its norm changes near the identity when you apply a group element that's very close to the identity. And may not be the way you learned it in calculus when you learn how to define the gradient, but it's the same thing, only the group is abelian. You basically scale the coordinates slightly, or you shift them slightly. And it's also not clear where this moment map lives. I mean, in the Euclidean case, you are in Rn, then this will give you a vector in Rn, the gradient. But really, this vector is a linear function. It's like the familiar gradient. And in the case of non-abelian groups, where it lives is in the Lie algebra of G, which I will not define for you, but maybe we'll see a picture in the next slide. We'll definitely see examples. Anyway, what you want is coordinates. In Euclidean space, the coordinates are given, x1, x2, up to xn. In general, in Riemannian manifolds, you get Euclidean space in every point, but it's not necessarily the same Euclidean space. But this gives you coordinates for describing the gradient. It is a notion that arose in physics. That's a reason for the historical reason for the moment studied in symplectic geometry. And what we already see is from the Maass theorem, is that minimizing the gradient, the moment map, is dual to minimizing V. And I want to stress that even though, the exact answers are, we have the duality theorem, when you are doing approximations, as we are, then this duality, is not exact. And an algorithm approximating the minimum of one doesn't necessarily give you an algorithm approximating the minimum of the other, and will develop algorithms for both. And lastly, I promised you, so I'll show you in the next slide examples that finding a vector with a zero gradient on the orbit is a scaling problem. Well, scaling is a name, but it will definitely, in the examples we've seen, you'll see that it is a scaling problem. So here are the examples. Here we have, the two favorite problems: matrix scaling and operator scaling, and the scaling conditions are written down there. Now you can just, the moment map is well defined. You can compute it. at a particular matrix A or particular tensor L. And you do that, and here's what you get. Amazingly, you get the distance to scaling in both cases. So when it's 0, you are scaled. Here, the moment map lives in, in 2n vectors, right? Because maybe not because, but anyway, that's a Euclidean case, and this is simple. And in the operator case, this turned out to be 2 Hermitian matrices, and this is also not a surprise. It's a Lie algebra of the general linear group or special linear group. Okay, so we see that scaling somehow is a natural problem from this point of view, even if you didn't have any other reasons to scale objects. It's the same with the tensor scaling, all the problems I mentioned also afterwards. Okay, so the moment map is 0 if and only if V is scaled. Okay, so now I want to get to the almost the last topic, one before the last topic. Any questions so far? Okay, so we want to understand this geodesic convexity and develop algorithms for optimizing in these geodesic settings, somehow generalizing the alternate minimization algorithms we have. Now, I should say that, of course, this is not new. Geodesic, convexity or geodesics and Riemannian manifolds were developed by Gauss and Riemann long ago, and they are studied and understood extremely well. And also algorithms in the geodesic settings are not new. There are even books written about them and lots of papers. And what I can say from all that I've learned is that they are somehow sparse on quantitative results, on convergence analysis. So what we'll do is give convergence analysis for, in this very general setting of any group action. And I'll explain, what it takes and what the bounds mean, roughly. So first, let me tell you about relating geodesic convexity to the classical convexity that you want in a very caricaturistic way. But that's all the time I have. Maybe this will deserve some longer talk. So in the commutative case, let's say the group is a torus, it's just an n vector, right? So you have Euclidean space, and in the non-commutative case, you have this group. It's GLN, general linear group over complex numbers. It's some manifold. It's a Riemannian manifold, and it doesn't look like a ball. You have to forgive my picture. It looks different, but anyway, the ball is or the sphere is another Riemannian manifold. And just in the picture you see, I promised you these tangent spaces which give you directions. So let me talk about these objects. So first of all, a direction in space, in Euclidean space, is just an n vector. And I want to point out, we'll use it soon, that e to the h is another vector. It's also an element of the group. And in the case of in the non-commutative case, then the direction will be specified by an element of the Lie algebra. In this case, it will be a Hermitian matrix. The tangent, I mean, if you take such a vector written in exponential form, e to the th, where t is very small, then you can see that it's, it just gives a gradient, it gives a tangent in direction h, and direction is, the same meaning in the non-commutative case. So we can start moving from any particular point And the direction we move, especially when we take derivatives, but in general, I mean, understanding the differential structure of these, the objects we are on, are geodesic. So geodesic from any point G is simply applying to G, moving it by an element close to the identity, multiplying by e to the th. So that's a geodesic in direction H from G, and you can continue it, and you get in Euclidean space, you get a straight line. In curved space, you get a curved line. But the point is that these are the shortest paths in this in the appropriate spaces. Geodesic is the shortest way to get between 2 points. In the non-commutative case, these are not all geodesics, but these are all geodesics we need. So I don't want to get to technicalities. But anyway, the point is that once you start thinking about convexity along geodesics, then all the notions merge. So in particular, define a convex function simply if it's convex in T, in this real variable, along every geodesic. So let's say you have an interval between 0 and 1. F is convex there if this is satisfied for every T. Okay? Just the same picture as we see in every convexity book or paper. And this, having convexity suggests normal algorithms. If you have, you want to minimize this convex function, if you have a derivative, you have a gradient, then you just go in the steepest direction towards your goal. So you start somewhere, maybe the identity, and then with some, and you compute where you are, what is a gradient, and you go with some small step, which is important to choose. You change it, and you get this sequence of steps as in the picture that hopefully leads you to the minimum. And there are second order algorithms. If you have access to a second derivative, to the Hessian of the action, then you can basically approximate your function by quadratic function and use this to get faster convergence. And there are books and books about them. And of course, you need convex functions, geodesically convex function. The first function we talked about is norm minimization, right? Well, it turns out that this function, just a minimal norm, so the norm, so for every point V, you can define this function on your group, which is the norm of GV. And this turns out to be convex and always, and it's very easy to prove. So we have convex functions, and we have convex tools, convex algorithms, and we can try to apply them. The main difficulty is, even how the action is specified. Basically, how do you know how convex your function is? In Euclidean space, there are these parameters which tell you how smooth the function is, or how robust it is, or they are defined in concrete terms because you have a basis. What do you do in general? And in fact, even how do you describe it? So I'm not going to get into all these details. I want to tell you basically the results and something about what they mean. So let's say we talk about the minimum of vector in the orbit, or the minimum, or trying to minimize or approximate the minimum of a moment map on an orbit given the vector. And we have general first and second order algorithms. In both of them, you don't need anything explicit. It's sufficient to have oracle access to applying a group element to a vector and to the function and to its appropriate derivatives, either the first or the first and the second. And the first order method is just the same as gradient descent, and it converges just like in the Euclidean space in the commutative case in polynomial 1/epsilon iterations as should be. And in the second case, this is much more complicated, and it starts from the first reference on the top, paper with Ellen Zhu and Garg, Lee, and Oliveira, was designed to do something else. But at any rate, like all second-order methods in the Euclidean case, it converges much faster, exponentially faster in polylog in epsilon operations. And as I said before, the most important difficult part is what goes on with this big O. I mean, what does the big O depend? And like the Euclidean case, it depends somehow on smoothness parameters of the action of the function. I mean, usually nobody describes group actions in the Euclidean case, and I guess one of the messages of this talk in general is that lots of things are described without groups, but groups are hiding there, and you know, taking them out and using what we know about them helps. Anyway, that's an important thing, giving the bounds there, and this depends a lot on the action, obviously. And what you need to do to analyze it is to understand the, you know, the irreducible representations of the action and compute the highest weights, and they give you, you know, after a lot of work, something that's very actually quite elegant, very simple parameters of the action that control this big O in this notation. Okay, I have one more topic for the last 15 minutes, and any questions for that? All right, so we have this geodesic optimization, and this happens. I described it mainly for the uniform scaling. I didn't talk about non-uniform scaling yet. I want to talk about it and what it leads to, because it's another absolutely magical thing and hopefully very important for applications. So I want to talk about non-uniform scaling and how moment maps give you moment polytopes. So here's our picture again. We have some group acting on a vector space, and use the moment map. And we already said that the null cone problem, or the uniform scaling problem, is basically the problem. I give you V, and you ask whether there's an element, ask you to find an element in the orbit, or the orbit closure, that has zero gradient, zero moment map. Okay, the non-uniform version is the marginals problem, or I mentioned, I mentioned it before. You want to scale not to the uniform marginals, but to other marginals that are also given to you. So I'll give you V, and also give you what the marginals should be. So, for example, different row and column sums in matrix scale. And it turns out.
Can I ask you something?
Yes.
So you said that whether or not V is in the null cone depends on whether there's another U in the orbit that has
zero gradient. Yeah, that's the first problem.
The co-NP thing. So if it is such a zero, then it's not in the null cone.
Yeah.
Can you shed some light on this?
The best light I can shed at this point is Farkas lemma. So I told you it generalizes the duality of linear programming, right?
Uh-huh.
So basically, this point with this zero moment map gives you the analog of separating hyperplane. The null cone is a variety. It's not a convex set, but somehow Well, it's not a convex set. It's a weird set. It's a algebraic variety, but you want to show that your point is not there. So what you get from a point with a zero moment map is the analog of a separating hyperplane.
I see.
Okay, that's the best I can do now. I mean, I can do more, but let me finish this. And okay, so that's really well, maybe we'll see something in the next slide that will make you even happier.
Thanks.
So okay, let me talk about the so I said the non-uniform case essentially is a problem that looks very similar. It just asks for a point in the orbit that has some other value, other vector as its moment map. So this is a much more general problem. So given this problem, you might as well ask the following problem. Let's look at the object that collects all the gradients along the orbit. Let's give it a name. Okay, delta of V. So what is this? This is all points, P, that occur as gradients on the orbit, right? I put this red star because to tell you I'm cheating, one has to mod out by various things, you know, mod out by maximal compact group, and you mod out by, you know, the Weil group, and you know, anyway. But don't worry about this. Essentially, delta of V is all the moments that you can find on your orbit. So that's a set. So here's an amazing thing. What's the structure of this set? It's a convex polytope. So this work arose in several contexts, and you know, it's true in vast generality, in all the generality we need for this work, all these group actions. It's always a convex polytope. Now, this sort of absolutely, well, to me, is absolutely amazing. First of all, you know, up to 2-3 years ago, the only polytopes I met over the many years, you know, let's say over 35 years, I never saw a polytope that was not given, you know, was not described either by vertices or by facets, or maybe a projection, something like that. But anyway, I mean, that's the only, you know, this is how polytopes are defined, either the convex hull of points or, you know, the common solution of linear inequalities, right? The intersection of half planes. And here you have a set of things that come out of nowhere in a non-convex world. By the way, here, when I say convex polytope, I mean it in the Euclidean sense. Okay? So somehow all these collections of vectors happen to generate convex polytopes. That's it's an amazing thing. And the problems I asked about, the null cone, the marginal problems are, you know, well, now you can translate them. You know, we ask whether, you know, some vector can arise as a moment map of some point in the orbit. Well, it's just a question of membership in a convex polytope. Okay, and the null cone problem is a question about membership of zero in a convex polytope. So this may help irrate your question. There's another interpretation now, right? You don't have to look at the null cone. There is some bizarre convex polytope. It typically will have exponentially many vertices, exponentially many facets, and so on. But at least this problem can be asked there. And it turns out that we can extend some of our algorithms to give the geodesic algorithms to give weak membership, to test weak membership in this moment polytope. Weak membership, I mean, to test whether a point is inside or polynomially away from being inside. Okay, so we can do that too. And maybe to finish, let me just show you how, how bizarre these moment polytopes can be, and then I'll wrap up. Any questions? Okay. So, yeah, so these are special cases, right? Take any symmetric matrix and look at all diagonals of all matrices that are similar to A, conjugates of A, okay? This turns out to be a moment polytope. Okay, it's not, so just to, if you think about the set of vectors, it's far from clear, although in this case, it's not that difficult to see that it's a polytope. So neither convexity nor linearity is obvious in these cases, and both hold. Here's another harder one. If we look at matrices A, B, and C, so that A plus B is C. Let's say we fix C and we look at all, A and B. And I ask you, what are the eigenvectors look like? Just triples of n vectors. Turns out that they are a convex polytope. I didn't get to discuss this, but I mentioned the Braskamb-Lieb inequalities. It's, things like, many inequalities that you know and love, like Helder or Loomis-Whitney, or, even some of the hypercontractive estimates and so on. It's inequalities that involve norms. And if you ask, what are all the norms that are satisfied by a particular type of inequality, they turn out to be a polytope. Okay, so this is one set. You see, I drew a line because these are objects that, sets. It's not clear why they are polytopes. On the other hand, they are polytopes, and it's not clear at all why they arise from this context. So, for example, I can look at a polynomial or a Laurent polynomial, let's say homogeneous. So it has exponent vectors, and I look at their convex hull. That's obviously a polytope. But this polytope arises from a very simple abelian group action on polynomials, basically scaling the variables. Edmonds polytope, so the matroid intersection polytope. I have two matroids, and I look at the convex hull of all indicator vectors of things that are of sets that are bases in both matroids. Again, it's a matroid, it's a complex matroid, and yeah, it's a moment polytope. So it's not clear why these are polytopes, not clear why these are groups, why they come from groups, but they are all moment polytopes. And as I said, we can optimize, not optimize yet, maybe just membership in all these polytopes. So yeah, hope this is useful. So let me finish because my time is practically up. So I will not do this. Okay, so yeah, we saw a lot. I think it was very heavy and conceptually, this talk. So I want to just say some highlights. One highlight is the richness of this, the fields interacting in this business. I find it quite amazing, and of course, I'm learning a lot. Another aspect that's really interesting is that the problem we started with, and many of these problems are algebraic in nature. And it turns out that the fastest algorithms we know for them are analytic, are these dynamic processes, these geodesic algorithms. On the other hand, to analyze these algorithms, of course, you need quite a bit of algebra. And maybe the most important point is that, groups or symmetries exist often, even if you don't see them. And if you find them and use them, this can be extremely powerful. Lots of mathematical tools that will let you use them. And for what to do, well, as I mentioned, some of the algorithms, despite polynomial running time in the parameters, are not solving problems because sometimes you need infinite precision. Well, we can, you know, test membership in these very, very large polytopes, moment polytopes. I don't have, we don't have any example of something new. So we can, you know, we can do matroid intersection, but it was known how to do matroid intersection. And I wish there were more combinatorial optimization problems that can be expressed as memberships in moment polytopes, that hopefully new ones. Yeah, geodesic optimization, I think we are just beginning to understand it. I mean, we are writing a 100-page paper to explain what we know, but I think that there is a lot to understand there. And finally, I want to return to the, you know, can you prove P different than NP or VP different than NP than VNP using gradient descent? So basically, we have these geodesic algorithms like gradient descent, and they solve null-con problems all over the place in lots of different kinds, and in particular, this non-commutative singularity problem. So what about applying it to commutative singularity? And this it took us a couple of years trying to understand why, you know, is there an abstraction to applying it to commutative singularity? And the most basic question is whether it's an null-con problem at all. Is the, you know, it's a variety, all the singular tuples of matrices, it's a variety defined by polynomials. Is it a null-con of some group action? And it turns out that, you know, I guess there are no tools we found that tell you how to test whether a variety is a null-con. You really basically have to understand the symmetries. It's a very general question of understanding the symmetries of algebraic variety. And finally, we did it with the Markham. At least we know there's some barrier, if you will, to PIT. We know that it's not a null-con problem, so it's not, at least the algorithms we have don't obviously apply to it. But maybe there are other algorithms, or more general algorithms that would do it. Okay, I end all my talks now with my book ad. You know that it's published, you know that it's free on my website, and you know that I like comments. Thank you very much.
Thank you very much.